Dear participants, I'd like to introduce you Aleksandr Farseev from University of Singapore, and he will perform the second tutorial of this summer school for the next 2 sessions for today.
Hi guys.
Hello.
How is it? So far, did you download any data sets? Did you try to play with it? Okay. My name is Aleksandr, but if you go back in US, ask Aleksandr, nobody knows who it is. Everybody call me Alex. You can call me Alex. Though in Russian it's not the same name, but it doesn't matter. So I was thought, what should I focus in this tutorial? Since we have so diverse and nice audience who belong for both social science and computer science directions, I thought not to be too technical, because that technology that I can explain in this short time wouldn't be too advanced for those who already know it. At the same time, I don't want to be too abstract, because if I were too abstract, then it wouldn't be too useful for you, because you guys need to work on these assignments and tasks for the following week. So I want to make it as efficient as possible. So I split my talk into 2 parts. In the first part, I'll glance through the common ways how people process the data. Why it's important? Because the data sets that we organize for this school, those that you download, probably some of you sign up already for certain topics. They all data sets. That means they have the data inside. And this data very often is multimodal and very diverse. We in our lab believe that we cannot longer assume that single data source is sufficient enough for any real-world application. So we believe that everything must be taken care of in a 360-degree view. So we work with multi-source data. This data is multiple modalities. It can be text, videos, locations, different types of semantics, sensor data from wearables. And this data must be properly processed. So the first part I will be addressing actually about data processing techniques. And the main aim for you is not to understand how to implement these things, because these things are actually available on the internet. You can find multiple libraries that can do that for you. But understanding of the principle is very important, because if you understand what this particular feature or data representation means, it will help you to draw good conclusions out of the data and out of your task, which is the ultimate goal of this school. We want to come out with meaningful conclusions, and we are not looking for results like, well, this model outperformed another one for 2%. And I don't know why, but yeah, we are very happy. So that's not kind of results we are looking for, especially in web science. So that's why I put it in this way. And the second part will be about applications on this data for different, mostly CS direction tasks, because our lab is more about computer science and social science. However, I will be asking you questions, and many of these questions I myself don't know answer, and I will be looking for your help. Because those who do social science, I believe they have much better sense than me what each thing that we obtain may mean. So I'll be giving you our results, I'll be telling you how we obtain that one, and then we can help me to understand why it's like that. So this is very interesting. I come here to learn, first of all, and then to share with you what I already did. Okay, so this agenda for the first part. So we're going through different types of data. The textual data, visual data, location data, sensor data, and of course how to collect this data, because, well, we can process it, but we don't know how to collect it. It will help us, we still cannot do anything. And visual data currently, just want to make some remark. It's very commonly processed by deep nets. And these deep nets, they being trained on some label or maybe some in semi-supervised manner, they can learn to predict something. So if you take one of the last layers of these deep nets, this deep net can give you a very high level of representation of the data, either for videos, for keyframes, or for image data. I wouldn't be addressing this here because of two reasons. First reason, because even we can get these values, we don't really know what is that. And it's not so useful in a one-week perspective. And second, because tomorrow will be another tutorial by a very experienced data scientist who work with neural nets, and I believe he will tell you a lot about how to work with networks. So he made my job a bit easier, so I don't need to address that. Okay? And yeah, all of us know that big data is not about data. Big data is about how to process it, actually. It was said some time ago. Important thing to notice here is that it was found by PEW Research Center that more than half users actually use more than one social network in their daily life. And they use them differently, and they achieve different goals by using these different social networks. It's not just like I want to register many places and that's all use. No, each of them help us to release some emotions, help us to communicate to others in a certain way. Like LinkedIn, for example, can be for very professional communication, or Twitter can be for updating some recent comments, and Instagram can be for sharing the pictures without even maybe any comments, just because we want to share something that we just seen, we was impressed by it. So all these data sources, they present users in 360-degree view. That's why they must be considered. So take example of Twitter, right? Twitter will be mostly textual view, but of course it's also diverse. There's some images inside there. Then Instagram is a image view, right? It's a visual view. For example, Foursquare, which is already not that popular, but it's still the largest standalone location-based social network. Will be giving you the view of location, and not just location. It will be giving you the POI, point of interest, which is related to the semantics of location, which in turn very much related to who we are, what we do, and so on. And of course, we have all of us have these wearable devices. How many of you have wearables on your hand? Oh, okay, not so many. And we can do one more research on this. Why web science people don't wear sports records? Maybe next. Yeah, so we have these wearable devices, and these wearable devices tracks us all the time. And being combining all these types of data together, we can actually get a 360-degree view on a person. And that's our ultimate goal. So it's Mr. Hammer, he's surrounded by the social network. Let's start from the textual data first. How many of you do NLP? Just to let me roughly understand. Okay. Yeah, so quite many. I'll just be briefly going through the basic concepts so everybody will roughly understand. So we have something called n-grams. N-grams is the sequences of words, and for n-grams it's important to have the exact sequence of words as well as their co-occurrence together. So basically, bgrams and single grams of just words is also the specific case of n-grams. And many of us are working with unigrams, not with n-grams. Because n-grams requires a lot of data. And I think for you it's probably obvious why. Why do n-grams require so much data to be processed and to efficiently work with them? Can anybody tell me? At least those who raise hand and say they work with NLP.
When you say a lot of data, you mean like a large corpus?
Yeah, we need to have a very large corpus to work with n-grams.
Because if you have a small corpus, many of them will have very low frequencies.
And if you like yeah. And if they have low frequency, why is it bad for them to have low frequency?
Models will predict better.
So this is in a computer science perspective. But I would say in social science perspective the same thing. If you have some multiple n-grams with a very low frequency, it doesn't make sense. We cannot draw much conclusion because everything we will find will eventually wouldn't lead us to any statistically significant result, which wouldn't let us draw any conclusion out of it. Yeah, that's correct answer. So, and the simplest model we can do is just uniformly distribute probabilities when we work with these words. A bit smarter way is follow so-called bag-of-word strategy when we compute the probability of occurring of the word. So basically just count how many times we see this word inside the corpus, and then it will be a probability of this word will occur. And also we can compute the conditional likelihoods. How likely this word will occur given another word. And one example is like a mythical unicorn is much more likely than mythical popcorn. So this requires general probability computation. And we can have the so-called Beethoven Grams models, and these models, they basically distributions of occurrence of a certain n-grams inside our corpus. And this is already very useful because this word clouds that we build to visualize our data, some simple models that we train in large corpuses for predicting something, many of them working on as simple as n-grams and unigrams, and this become much more useful than some very sophisticated techniques like word-to-vec and so on. So if it's something simple, doesn't mean it doesn't work. I would say that large data is sometimes much more crucial than the complexity of the technique itself. And then, how many of you know this guy? His name is James B. Pernbacher. Anybody know him? Did you heard about LIWC? Okay. So LIWC is a dictionary that was invented by this guy. This guy himself is a linguist, and he was studying how does word usage reflect our personality, how the words we use is related to our personality, to the way we behave to other people, and the way we behave online, offline, and so on and so on. He wrote a book called The Secret Life of Pronouns, and just that book is very interesting already because he's finding some very interesting relationships, like people who say I all the time, they actually followers most of the time. And those who say we, they actually leaders potentially. There are also a number of words that related to angriness, or the number of words related to war, and so on and so on. So what he ended up, he's creating the dictionary called the LIWC dictionary. And this dictionary is just the word, and basically just a set of words that are meaningful to distinguish one type of personality of person to another. So he found these crucial words that degrade personalities the most, and call it LWC. It's 69 categories. Recently they came up with something called LIWC2. It's a hierarchical structure. Well, the first version is just a dictionary, so all of them have the same level. But basically the idea is always the same. So it looks like this. Every person represented by a text can be represented by a histogram of occurrence of different types of words. Here is not all corpus, of course, it's just some example of people. And just by using this histogram, we can look for people who are similar to some potential of being extrovert or introvert, for example, and some other personality aspects. Maybe some of you study this better, so you can tell me how exactly it can be used in social science perspective. We were using it in computer science perspective. So we were training models, and we found that models being trained just on LIWC can actually outperform many sophisticated techniques we can work with for the natural language processing. And it is very easy to use. All of you can just go download this program called WWC Lite, and you can run it in a corpus and get a distribution of given a corpora just right now in 5 minutes. And this is already a very meaningful representation of a text. So I wouldn't be teaching you to do this. You have multiple technical mentors. All of them can help you easily to do that. And also, there is a version of the dictionary itself uploaded on the internet somewhere. So you actually can just download it. Somebody already created the program. So. But I didn't say that. Okay. So, and then another meaningful meaningful thing. I also wouldn't be going too much into detail. What is important to mention is topic modeling. Topic modeling basically is a family of probabilistic generative models that, without training data, can tell us the distribution of documents among the topics. What is document? Document is a set of words, basically a bag of word model. So by training this generative model, for example LDA, one of the most popular ones, iteratively, and feeding into the distribution, you eventually can get the distribution of this given text among some latent topics. So it's not topics that we define. These topics will be eventually coming out, so our job, our next job will be say what each topic means and how to say, how to label these topics. We also have the distribution of topic among the words, and well, just remark, word is not necessarily real word. Word can be wherever token, wherever thing, from wherever type of modality, not necessarily real word. So give us distribution of this topic among words, and by seeing which words are the most popular in this topic, we can give a name to the topic. For example, this topic is about food, this topic is about travel, and something else. This is another very powerful thing to study the data. And I believe many of you may consider to use it during the school because it's extremely easy to use it by tools provided by our colleagues, by tools you can download from internet, all languages supported, wherever language you like, you can just find it and run. And you will get which topics are inside your text. It's very useful to understand because topics are much higher level structures compared to the words themselves. So you can understand what actual components of this text generated by people. And again, I wouldn't be addressing this too much because you'll get another tutorial 2 days later by Professor Aleksandr. She will be telling a lot about generative topic models, am I right? Yeah, so just, I'm very lucky. I mean, most of the things I don't need to tell you because we have another. So I just take a part of giving you an overview and to make you have a good start. And this is just example. So we have 4 topics here, and each topic consists of some words like brain, neuron, nerve, and life, evolve, organization, and they have probabilities of this topic, of this word occurring inside this topic. So by taking these top few words, you can actually give a name to the topic. For example, the third topic will be about brain, about neuroscience most likely. The last topic will be about data. This is a typical example of a document. This is a proper document, not a Twitter. For Twitter, they have models that are able to work with very short text. For example, one of them was developed by Singapore Management University a few years ago called Twitter LDA. So they try to handle that issues by regularization. And there are multiple tools. And here in Russia, they have something called bRTM. That one, also variation of topic models, is able to work with multimodal data. It also can be downloaded and used. Just Google it, and you can ask me, of course, later if you find something useful for you. And here we have an example where each Twitter user, we sum up all his text in Twitter because it's unreliable to use single tweets that are too short for model to provide reliable results. So we sum up all the text, or maybe text always some long period of time, at least 10, 20, right? So we get a document, so each user is a document. Then we run LDA model on it, and you get the probability distribution. So each user will be a distribution. And this distribution, again, can be used for social science, just to understand who these users are, to find the similar guys, or can be fitted into the model, because models, machine learning know how to work with this kind of data. So take a note about it if you didn't try it before, and those who try already, I believe they love the data, so I will for sure try this later. And then, of course, we can also come out with some heuristical features. And for example, as I'll tell you later, for example, for gender and age detection, these heuristical features are extremely powerful. They are manually crafted by men. These features belong to social network features as well as some linguistic and stylistic features. For example, it can be number of hashtags, number of slang words. We use some slang dictionary to find occurrences of slang words, or for example number of URLs. The interesting ones are the sentiment scores, sentiment level, which is the modular of the sentiment score, plus misspellings and mistakes. Interestingly, people of different age and of even different BMI have very different characteristics of how many mistakes and misspellings they do. And this is one of my biggest favorite questions that I'll ask social scientists. I'll ask you the same question later, which is the relation between your body mass index and number of mistakes you do in text. I have many assumptions, but really it's so interesting, and so I want to know your opinion a bit later, maybe second part of the lecture. And then we go to the visual data. Anybody do visual data processing here? Anybody? Any visual data, images, videos, keyframes, anything? Okay, computer scientists, raise your hand. Okay, so social scientists as the rest, I assume. Okay, and somebody probably belong to both fields, right? Okay. So this another a bit old-fashioned way to work with images, but it gives you a good sense of understanding actually what kind of data representation can be given from the images. So we have an image here, and we can detect the directions of the edges inside this image. Edges themselves can be detected by the image gradient. Basically, it's related to how fast the intensity of the color change. So, like if we have a picture of a cat here, I don't know, do you see or not? Then, by taking gradient of this picture, you can get actually the edges of the cat. And these edges have a direction. So, if we split the picture into the segments, then each of the segments will have certain direction from 0 to 360 degrees. So we can split this sentence maybe in a larger segments, and then for each segment count the most popular direction. And we will build a histogram from 0 to 2p. This is a very basic concept, and with this kind of histogram, which is an array of values, which is a vector, we already can do a lot of other things, and we feed in machine learning models. We can look for several pictures for information retrieval. We can try to understand, for example, what this group of pictures have in common, so that in terms of edges, these pictures are very close to each other. And then we may find that these pictures are taken by people of similar gender or personality, or people who have similar friends, similar behavior. These kind of things are very interesting to discover. If you guys want to do some research on a cross-source, cross-model direction, this will be very interesting. I myself doing this research already for years, and we can do a lot of things to discuss. So, as just this example I use, so we have these 4 quadrants, four regions, and each of these regions distributed is basically a histogram, and this histogram is about what is the directions of these images inside there. So this is the representation of the whole image. So, but this thing is not that useful for us, because if most of the times we will be taking very small regions of the picture, and then we can get some kind of bag of visual words, bag of visual words set that will be related to this image. It will be enough for machine to understand which images are similar, but for us it will be too meaningful. So a bit later I will tell you actually what else we can use for this to understand the content of the image and the meaning and the semantics of image much better. By now I need to introduce one more concept to you called the SIFT. SIFT. Anybody heard about SIFT, SIFT? Huh? Good. I hear somebody heard about SIFT. Yeah, so basically idea here is not too far from just the directional histogram of images. We take these images represented as histograms, and we perform a clustering of them. And this clustering can be any kind of clustering. One of the popular ones is the hierarchical K-means clustering. And then we can get groups of these images that are close to each other. So we then say that these groups, these clusters, are called visual words because they are larger and they are countable, they are quantifiable. So with these visual words, we already can further work, and it's already much better. We can have much better understanding what is this inside the picture, rather than just working with some very low-level features like edges. So just example of the clustering. Okay, does it work? Okay. Yeah. So we have multiple dots. These dots are our low-level features, and then we keep dividing the space till we get the final result of the clustering. And these clusters will be our visual words. So we can further work with these visual words. We can get this kind of tree, and this will be already the visual word tree. And this is already very useful. If you look inside the visual words, you can see many things. Libraries you can work with for this is OpenCV. I don't know, did anybody work with it? One of the most popular is OpenCV. You can work with this thing. Yeah? Okay. Okay. So, yeah, we got these concepts. So, and then we summarize, represent the image as a histogram of some, but not histogram of something low level, but histogram of the visual word, some high level concepts. You can go a step further and make it even more nicer for human to understand. So now we have a picture. Sorry, it's a bit too blurry in this screen, but it's okay. By the way, this guy is a Merlion. It's a main symbol of Singapore. I come from Singapore, so I must put some picture in Singapore landmark, as my professor will later school me for this. Yeah, so here you can see the statue. You can see these green circles. These green circles actually is detected objects, and these objects are trees. And trees is a visual concept. Tree is something human already understand. So this is the pictures with many trees, and maybe with a statue, maybe with the people, and maybe with the stairs. So we can see the distribution of the concepts. So it actually looks very useful if computer can run some algorithm on millions of pictures fast and tell what is on each picture. And this works surprisingly very, very well. The latest models are neural nets models. So it's usually, they don't work with SIF descriptors, they don't work with data directly. But even by using SIF descriptors and the representation of the data I showed in the previous slide, you can get very nice result as simple as by using SVM. How many of you know SVM? Yes. Good. Okay. So basically it works in this way. We have some learning. We combine these images in the form of a web of words, which is a clustered edges of these images. And we feed in some model. This model learns how to predict certain concept. For example, tree detector, or rabbit detector, or whatever concept detector. So now we have thousands of these kind of models. We run our image on all of these models, and we can get distribution of this image among these concepts. And surprisingly, this one also very nicely available. And in our lab, we also made the API. So all of you can actually use this API, sending us an image, and immediately get the distribution among concepts on this image. So you can utilize it in summer school. You don't need to go too deep to work with images, you can just use it. I will give you a username and the password later, so you can try that. Also, you can give us feedback about our API because it's just an alpha version, very early stage. Yeah?
Just a question.
Yeah?
Is it available over the web, or we can integrate it as well?
Again?
The API can be integrated to other codes as well, or it is available on the web?
Yeah, it is. It's RESTful API.
Okay, it can be.
You can use it as a service. Partially the technology inside is published in our papers.
Mm-hmm.
We have more than 20 papers around this thing just in a few years before. But the best way to use API, just use it as a service from our platform. You can use it for free. And
I'll
give you no problem. I'll later introduce it. And so basically this can be handled as a classification problem, and then if we build some zebra detection model, it can detect zebras from non-zebras. And then we will have another 999 or maybe another 10,000 concepts, And then we can get a model that can tell us what is in a picture. And then we can build a distribution of what is an average on the pictures of this user. So now, in a matter of few milliseconds, we can get complete understanding of who this person is based on what data he posts in the web. And it's very strange not to use this kind of opportunity. So I'll tell you later how we do that. Well, and more will be told by Andre tomorrow, I believe, about generally machine learning techniques on this. And then the next one is location data. Location data is very broadly available. There are many sources of location data. One can be the explicitly indicated location. For example, it can be the POI tagged by Facebook or Foursquare or any other social network users. They are checked in here, so you'll know what this location is. Another source of location could be the metadata of the image. Sometimes the camera saves the location information inside the image. Another source of location can be these locations available provided by telco companies. They basically say they give very long tracks of rough location of the user, but you can still understand roughly how these people move in the city. So all these telco companies, they make use of this data a lot to solve some business problems as well, like distribution of advertisement and so on, as well as the problems of same as problems related to some government, like for example, planning of facilities and so on and so on. So you can see that if in some area people travel very far all the time, it means there's not enough facilities for them. In some other place, they may be too lazy and too fat, don't travel at all. So maybe it's too much facilities. Maybe we should cut something there. Yeah. So there's many social networks for this kind of data. And I believe the very first one was called Dodgeball. And these guys was doing exactly the same as Foursquare, but then they were acquired by some other company. So the founders of that Dodgeball give all the code to the company that bought them, make a copy of this code, call it Foursquare, and make one more server that eventually become popular. So Foursquare was not the first mover, but the founders of Foursquare were first movers in the location-based service domain. And then everybody picked it up, like Google, like Facebook, everybody wanted to put this Instagram as well, which gives us a very large pool of selection where we can pull this kind of data. Main competitors, main providers of the service can be considered Facebook and Foursquare, but yeah, Instagram, which is part of Facebook, also contributes a lot to this. So it's a different types of data available in social media services related to location. Location is social media services. It's not just location itself, which is not too useful, especially if it's sparse. But it's also social relations of this guy, those with who he drinks beer and so on. Then temporal relations, which how he moves in the urban environment as well as how he posts, which is also his mobility, just virtual mobility. Then is geo data itself, which is longitude, latitude, and is some communication of this person with others, reports, retweets, as well as his social graph. So location-based service is a very sweet type of social network that, except for normal social network attributes, has a very nice feature of giving location and semantics of this location. So how we work with that? The most obvious and very powerful way, and is applicable to all of you again, is just take a guy from the data set or from social network itself, download his or her check-ins, and then represent this person as a distribution among categories of these check-ins. Of course, we can distribute among actual places, but it may happen that the vector will be very large, because the distribution must be the same for all users. And it will be very sparse, so it will be the same problem as with n-gram and small data sets. But if we use the categories of the social network, in Foursquare particularly, we used to have 764 categories, but I believe now we already have more, maybe 5 more categories. Ivan, you told me last time how many categories do you have? Oh, so this is updated. Okay, yeah. So, and these categories as a different types of places where this person visits. So his snapshot of his location-based social network activity gives us a very nice picture of who this person is based on the places where he goes. And one of our students, she actually found that just by monitoring where a person goes and the time where he goes, can easily tell does this person have a boyfriend, girlfriend, or married or not. It is just very simple to tell that thing. And that inspired us for another research topic, and that research topic gets very famous. I'll tell you a bit later. But in general, this is very powerful data source as well, and all of us must know that just having a lot of data and just applying some models on it is not enough. You must think a lot about what type of data logically can be useful for what type of applications. And this is where social scientists must help computer scientists, because computer scientists sometimes are too fast in modeling and too uncareful in thinking before the actual research starts. So then another way, make it even more general, is apply the topic modeling on it, right? I told you about the LDAs. So here, the words will be location categories. For example, I visit train station 2 times. It will be, my document will contain 2 words, train station. And then I visit, for example, airport 1 time, so I will have 1 more word airport. So all my activity will be number of words. And these words, of course, in terms of topic models, it doesn't matter which word follow what, because it's unigram. But yeah, we can go to more sophisticated case and just try to monitor which location follow which location. Then we can put spatial components as well, and then become even more interesting. But generally, now we have 764 categories, and we convert them into some n categories which are much smaller than 764, like 10 or 20. Each of them will be a set of corresponding location types, and we can say what general topics, location topics of this person. And again, this can be done very easily. 2 steps. First step, get the data and compute the distribution of the locations. Second step, run LDA. You can run any conventional LDA. Now we can get some very interesting representation of data. All of you can make it in maybe 1 hour, no problem. Again, how to make it, I wouldn't teach you. I will tell you something else, but it's really easy, and ask all of these mentors, they'll help you in this. So, and this is an example, right? So we have, for example, 6 topics. And this is from real data from NUS MSS dataset, one of the datasets provided to you. So we run it on all users, of location data of these users, and we get these 6 topics. 6 was determined empirically, just topics made sense. When you go a bit higher than 6, some topics become not too useful. And also it can be determined by something called perplexity, but perplexity also not always works well, so there's many ways to work with it. Just try to play with it and see which one is the best for you. So here you can see topic 1 is about Malay restaurant, mall, university, Indian restaurant, Asian restaurant, so many restaurants, different types of restaurants. So we call it food lovers, for example. And then we have travelers topic, poetry, wars, family, guys, students topics, and some teenager youth topics. Well, teenager means not the age, teenager means the lifestyle of teenager, of course. And this just 3 users randomly sampled from the data set. You can see distribution of each of them among this. Here's an example of, it's 6 topics here. You can see the distribution of each of these users among these 6 topics. So you can see some people are very different to each other, so we can distinguish them easily, and we can really do large-scale data processing. You don't need to do any more manual processing. At the same time, we can do very nice social science or computational social science research on this. We don't need to go to technical as well. And except for that, of course, we can utilize the location data itself. For example, we can use something called area of interest. Area of interest is a cluster of locations where we go often. And if you do this kind of clustering, it can be spatial clustering, maybe some DB-scan algorithm or some other algorithms. Google, maybe spatial clustering, or maybe geographical clustering, something like this. You can get these areas of interest in the map. And the largest, most popular area of interest, most of the times will be either your home office. So users, they no longer, we don't need to ask them where they live or where they stay. They already know where they live and where they stay. And then out of this location of their home or office or some place they go often, for example, parents' house, we can know the places where they go, correspond to this area of interest, as well as the number of these areas of interest, as well as number of outliers, so how often people like to discover something new, which is again very related to personality, very related to job, to many things. And we can say the distance. Some people like stay in a very local place, go eat at the same time every time, and they maybe don't travel far from their work as well, from office, but some people like really travel a lot. And these kind of indicators can distinguish them very well. That's very useful. And then Dr. Nolas, he will be presenting on 6th, right? Yeah, the 6th of July here in school. He's done a lot of research on location-based services. So this is a picture taken from one of his papers. So he monitored what type of features fluctuate with the time and space, and which doesn't fluctuate, so they are more or less stable, so it can be used for training some predictive models. Again, these features are very simple. For example, how the popularity of the place, the physical distance from person tend to go to a certain place, and maybe the place of day, the hour of the day. And here you can see the weekdays. So you can see those ones that are stable, those are good features to train the model. And those are not stable. They, at least you must consider this temporal aspect, because if you just train a model on Sunday and then try to predict Monday, it wouldn't work. So, and this type of features also very useful. So they can be used to study the users, to do quantitative and qualitative analysis. And then we have the sensor data. This is something very recent. I'm very happy to open this because we managed to get very large sensor data sets. That one that is provided to you called an US Sense. That data set is about 140,000 workouts of the people. And we are currently working on another data set in the US. That data set is about 15 million workouts and several million of users. So it's really representative data of the whole world. That one we didn't release yet because we need to get our publication first. So we will release to publish as well. But that one that we have already very large. In fact, that one that we have already largest in the world, especially considering that they have all other social networks inside. I'll talk about the data set a bit later in the end of the second part. So how to represent sensor data? Well, because some workouts of people, workouts consist of semantics, which is a type of workout, for example, running or jogging or doing some gym exercise. And just presenting user again as a distribution among this activity type already very good thing for training a model. The same a very good thing to understand what the whole population of the data set. So want to work with sensor data, look at this first. It's very semantically rich thing because we don't need to predict. We definitely know what type of exercise this person is doing because it's self-annotated. Person says what he's doing. Unless person doing running and doing actually something else and try to trick us, but data set is sufficiently large, so we're not really bothered about that. Yeah, so we can get this kind of distribution. So the idea is the same as in the previous types. And another way we can do is actually work with actual sensor data. It's the changes of location, changes of the altitude, changes of the heart rate. We have a heart rate data inside. And how we can do it? We can move it to the frequency domain. So who knows how to change the sequential data, move it to frequency domain? What we need to do with it? Any simple way? Basically, what we're looking for here is to get the workouts of different lengths. Some consist of 100 points, some of 1,000 points. to be represented as a fixed size vector. No, for those who study simple physics or math, they know that there's such thing called Fourier transform, and the fast version of Fourier transform. We can project the sequences of equations or sequences of whatever thing into one representation of one frequency representation, one spectrum representation. And then we can work with these spectrums, further distributing them among means. So now doesn't matter how many data points in our sequence we have, we can represent them, for example, as a vector of the array of 100 or 200 or whatever. And so we can do it for each of the modalities of the data, and then we can get the full representation. Let me know if somebody wants to run that. I have a Python script. Maybe not everybody will be working with sensor data, so I didn't upload it, but I can just pass to you. You can run and get, from raw data, you can get fixed representation of this data from the vectors. And of course, we can count number of locales, average hash rate, ascend, descend. You can see the age and gender of these people, which doesn't repeat in this group, but I put it this out because it's useful representers. And we can get the oxygen consumption, which is actually not measured by center, but it's approximation computed based on the speed, the slope, and the heart rate on that moment. And it's another bunch of research thing, is it accurate or not, but we just use it because we train the models on it, so we need some nice representation of the oxygen intake and consumption for the person, which is directly related to your health and fitness status. So this is just the overall picture. We have textual features, location features, image features, and sensor features. And each of them, these features of data representation, are very, very different, very diverse. So in machine learning, in the computer science perspective, one of the biggest challenges here, okay, given so diverse, incomplete data, how can we train the models to make use of it and make it actually work better than if you train on a single data source? And when we come up with this idea, initially many conventional scientists were doubting that it will work. They was using some single sources, like some labs still keep working only on text. But I would say, based on my experience and all my papers, I definitely can say that single source data always work worse in terms of prediction or recommendation accuracy compared to multi-source models. And it's easy to explain. Well, first, it's not as the data described users in very diverse view. Second, just much more data. If we utilize visual information, it's like if human will close his eyes, stops smelling, and close the ears, and then you'll start arguing that he actually can sense the world better than those who do all these types of senses. Okay? So, basically, we're talking a lot about data. And this data is, we basically have assumption that this kind of data is available to us. So our basic assumption is like this. Okay, now we have the data sources, data points, and what is very important is that we have the mapping between user accounts from one social network to another social network. So we know exactly who this user is in another social network. There is also another researcher who is trying to map this automatically, but we don't address that. We need to know how to find exactly the same user in different social networks. So I want to ask you, how would you do this? If you have multiple social networks and you want to map one user to another, and you want to do it in a reliable way, so you don't want to get too many false mappings.
Look for the links and profiles.
Again?
Social media. Look for links on other social media profiles.
Look for names.
Links.
For links.
Yeah.
User personal information.
Yeah. So sometimes people just leave a link on the person's profile in another network.
Okay. Well,
Assuming the same behavior.
any other ideas?
user personal information which is available publicly on the social network?
Yeah. Well, so if you go to research on how to map these users to each other, they have many techniques. They, for example, use user names, and they say that a very big overlap of user names exists in different social networks, so we can map, or we can train some models, we can try to predict whether this user belongs to certain social network or not, and try to find the similar users in different modalities, and this way to map them one to another. Then there is another very, very reliable way. I didn't put it in the slide, but I need to tell you because some of you may utilize it in your research. There's web pages, one of them called, for example, about.me, about.me. So very interestingly, people go there and they just explicitly post, this is my Twitter, this is my Facebook, this is my LinkedIn, and so on and so on and so on. So basically, they use it as, should we close the window? Do you feel cold?
Please close it.
Okay. So people basically try to make their online identities diverse, online identities to show who they are, and they do this for different purposes. Some people are very public, so they want to refer to their actual accounts. They don't want to refer to fake accounts. Some other people, they want to draw more connections, so they use this web page to try to know. Some other people just have fun, and they found that many of users of this about.me web page and other similar, they are certain bias in demographics. So it's usually young people, those who don't take care of privacy. But of course there are some examples from older generation. Like I know one researcher in computer science, very famous. He doesn't have any social media accounts. I meet him in the US quite often. And then I know his friend in US who have all possible social media accounts. And that's the first professor. He always gets published by another one when he visits him. So even though he may not want others know where he exactly, another professor always put a selfie with him so everybody knows where he is.
Who is he?
This is one of US professors.
Oh,
okay. US professors. And another one is a professor from US. He's doing also social media analytics. I mean, both of them are famous. Yeah. So it's like this. And the problem of demographic bias didn't let us use this straightforward approach of using this kind of platforms, because if you want to predict some demographic attributes, for example, age and gender, and it doesn't make sense for us to crawl the platform where everybody is 10 to 30 years old and we don't have anybody older. So we follow the idea that was proposed as the first version of how to do it. We monitor the so-called cross-linking activity of users, where one user posts something in another social network about himself. We were using these four social networks because each of them is a very bright representative of a type of the social network. And the idea of problem is like this. We have many social media accounts. Many people repost their posts inside Twitter. And the funny thing is that if you, like in Instagram for example, if you tick that you want to repost, later Instagram will never ask you, do you want to repost again? It will just by default repost everything you post. You may forget about that, which is not so good for privacy of the person, but very good for us, the researchers, because we will get not biased by this fact, and we can really get those pictures that person may not want to be released. And we crawl them in this way. And for example, the Endemonta network, which is a very recent data source, I recommend to all of you to try it. It's a very nice data source for censored data and so social media activity. We introduced it in our recent OIS paper. Idea is like this: you have some workout for some guy in Endemonta, and then we have some random guy, somebody. I don't know. And then what we can get the repost of this guy in his Twitter. And this Twitter can be monitored by some crawler using some legal way like API, Twitter Stream API or Twitter REST API. And every time this guy reposts something on Twitter, we can monitor him. In the case of Foursquare, for example, we can only crawl those posts that are republished to Twitter because Foursquare doesn't let us crawl their posts themselves, which was true about 6 years ago. They actually let people do that. So Mr. Nolas was lucky to get his very large data sets on that time, but currently researchers don't have this opportunity, so we only have to use those that are reposted to Twitter. But for some other social networks like Endamondo, like Instagram, we actually can get the idea of a user go crawl everything for this person in a original web page. So get the whole timeline of the person, get very, very large multi-source data sets. And that's the beauty of this, and I encourage all of you, if you consider to do research on this kind of application, do it multi-source. It's the future, and it's obviously will be moving to that direction. Also, I'm not mentioning the video, but video is another extremely popular type of data, and Professor Tat-Seng tomorrow will be talking about that more, so I'm lucky again going to talk about that. So, this is basically the idea. And this is the second part of my talk, because first is much shorter than the second, but I will start it a bit, so you will have more time for questions in the second part, as well as I will have time to describe the data sets, and then I'll ask my other colleague to describe another data set that they will work together with more, so you can get comprehensive overview. And tonight you're already very, very well prepared, and you can actually start working. How many of you, by the way, found your groups, know who's in your group, know the people in your group? Anybody?
Still no.
So, like, we have this table, right? Inside the table, do we have a lot of people sign up for the groups already?
I can see there 1/3 part of all have signed in the table in the spreadsheet.
Okay, guys, you have this very boring tutorial by me, so you have very good chance to sign up to a group at least. Right, so you can use this opportunity. So by evening, when we will be producing the data sets during your lunch break, we expect everybody roughly know what they want to work on, so it will be much easier for us to help you and much easier for you to start straight away. So tonight you already can get some initial results, so tomorrow when we come back, our mentors, our helpers will know exactly how to help you, so make it the most efficient. So let's make this Russian summer school the best, most efficient summer school all over the history. Because I'm from Russia, I'm interested in it. Right? What is the best summer school? So let's see the results. So everybody will come up with a paper in the end. Okay. So here just a quick recall. So when I'll be talking about profiling, I'll be talking about different applications that can be achieved by using this kind of multi-source data. And of course, the models that we're using are not that simplistic. If you want to understand any details, please go to my academia webpage, which is NUS academia.edu/Farseev. Farseev. Or you can just go to my personal webpage, all papers are there, just can download and read. But I will give you a sense of what type of models can be used to get some very meaningful results in different domains, in different sub-applications of this field. And then I will talk about some business implications in the end, as well as conclude the whole talk. And I will be talking about data sets in the end as well. So everybody must stay till the end, otherwise you will miss some data set introduction. All my slides will be available tonight on my webpage, and I believe in the school webpage as well. I probably post a video as well that I'm now shooting. There are some interruptions, but
It's okay.
hopefully you will understand everything, as well as the screencast of this talk. Okay, so how many of you know this guy, okay? Maybe we are politicians, more politicians than social scientists and computer scientists. Well, why I start from him? This is an interesting story. One of person sitting here, she decided, well, I worked on social media data last time, and I found that it's so nice to monitor social media users by where they go in terms of locations. Types of places, as I said before, the type of places you visit reflects your relationship status. Except for she is monitoring her boyfriend in this way in social media. She also decided to do research on it, so she extended and started work on multi-source learning for relationship status prediction. I didn't include this paper inside there. You can read this paper in AAAI Proceedings 2017. And also this one inside our API, so you can use this model to predict relationship status. The funny thing is that after we published the model and published the paper, somebody decided, well, let's run this model in the politicians. And they run this model on two politicians. One was this guy, another one was Barack Obama. And in case of Barack Obama, the marital status was detected correctly. He's married. But unfortunately to Trump and to the whole world in terms of Trump, it was detected wrongly. He was detected as a single. And journalists take care of it so well. So after we published this paper, about 60 articles all over the world from China to US start publishing that even AI thinks that Trump is a bachelor, he is single. No wonder he treats his wife in a certain way. That's why AI detects. So, of course, in my perspective, the reason is because when they run it in Trump's profile, they only run it in textual data. They didn't utilize other data sources. The first reason why detect wrongly. So the reported accuracy of 86% was reported for multi-source data, but they run it on the textual data. And the second is, I believe, a lot of tweets on Trump's account actually from his assistants, not from Trump himself. So it could be some young guy or girl who indeed single and model actually predicted correctly. Yeah, so that's actual explanation. But I found it very, very funny to talk to journalists and discuss why AI thinks that Trump is single and how it's relevant to other opinions of the crowd and the public. So you can Google Trump bachelor, you'll find all these articles. It's very, very, very funny to read if you have free time. But you need to solve your assignments first, okay, before you read this kind of thing. Yeah, so basically what is user profile? User profile can be many, many different things. It can be the demographics of the person, it can be his location representation, the affiliation to some user communities, social graph, sensor data. And since 50% of users, as I said already, use more than one social network, at the same time, these social networks represent persons from a very diverse view, and they let this profiling to be done in 360-degree perspective. That's why we call it 360-degree user profiling. You can find a paper called 360-degree user profiling. That one is more survey paper about generally our vision on this. Yeah, and in our other works, except for that paper, we address different issues of user profiling, different components of user profiling. There is individual user profiling and group user profiling. Individual user profiling in our works consists of some identity profile as well as some wellness profile, or we can call it physical profiling. So identity profile in terms consists of age, consists of gender, and consists of our recent work on personality, which is not published yet, but is submitted to one of the conferences, so it's under review now. So if some of you reviewers of the paper, let me know. And then wellness profile is we was working with some weight-related problems with obesity things. And then we have a group profile, which is groups, user communities. So all these things in terms of attributes also form a 360 degree, and it's all from multi-source. And the whole overall framework for business or just framework for research can be look like this. We have social media users. These users have social media data as well as physical data from sensors. Then this group, this data can be, we can detect groups of users based on some algorithms, some cluster approaches that we develop, as well as some individual attributes of these people. So we use two algorithms that we proposed recently. So we have the full representation of these people. We have their community affiliation, as well as their some demographic attributes, as well as their physical attributes. So all these can go to platforms. These platforms called social discovery or social listening services are quite popular, though not that comprehensive, but it is quite common in the business industry. And they can provide the view of people on the world. So, for example, if you have a brand, you sell something, you can find those who mention this brand inside social media, and then you start monitor these people, and you can get communities they belong to, demographic attributes, their even physical attributes, everything. Just imagine how sweet it for those who own a brand, how nicely they can readjust their marketing and advertisement policies in order to reach some goals. So we actually have one topic in our topics, it's about the business. So those who sign up there, I expect you guys not just producing models, they're doing something but you know why and for what it is. I want you looking more into where it can be useful, some business cases, maybe some market of this. Of course, you can do full market research and everything this week, but as long as you come up with some very nice idea of how it can be used, is already very good. And you know, this research direction recently get very popular. Even ACM Multimedia this year have a workshop on business application of multimedia. So if you guys can come up with some nice business idea now, after 1 year you can get first round papers there that will they even forward it to VCs for potential founding members. So it's very nice option. So, and the data, I'll just repeat why I repeat here, because those techniques that I presented in the beginning, they are general. Out of those techniques, we took some that we are using for our models. And these techniques are more or less similar to those machine learning models that we train among most of our works. So I just summarized it here once, and later I wouldn't touch data. I will just touch the machine learning part. It's still an application of it, so you can just learn about it. And also, later when you read it, also you can comprehensively learn about data sets, everything here. So that's why I also tell you here that, wow, you cannot see at all the links, but you have these links in your document.
Yeah, that light, if you close that light, it will be visible.
Yeah, who knows how to close the light? You're ready? Yeah, do you know how to switch on the light? Yeah, sure. That's a good idea. Yeah. Oh, this is a gate?
Yeah, that one. Yeah, gate one.
Oh, like I said, maybe the gate light was
It is.
oh,
That's
very private atmosphere. Maybe in this kind of atmosphere I can speak longer. That's always my problem. Short, no problem. Long, too long is can be a problem. Yeah. So it's related to these two data sets. One is a US MSS, another one is a US SEND. Based on this data set, we publish at least 3 high-rank and many supplementary papers on this. So we kind of very well study the data. You can ask me personally or some of our mentors on the data set. And all I will be speaking forwardly will be related to these two data sets. Just following maybe 6 slides summarizing what type of data processing approaches we use to feed in into machine learning models. So for text, we use 69 LWC categories. Let's have a quiz. What is LWC? Who remember? Frequency of usage words related to personality. Yes. Well, this picture tells you everything, but at least you wake up. Yeah. So the second one is topic models. We use LDA and we determine number of topics based on the perplexity values. So when the slope of perplexity, not the slope, but the shape of perplexity values change, we treat them as optimal number of topics, but this is just one way. Many other people just heuristically look into topics and say which number is the best. So most of the times it was 50 or 51 or 40 something, so we just keep it 50 most of the time to make it more or less uniform, so we can use different data sets for different models, so we can flip them around, so it will be more efficient to work with it. And then except for that, we have manually crafted features, and these features are hashtags, number of hashtags, number of words, number of URLs, user mentions, the average sentiment level, which is detected by our own sentiment engine, is based on the conventional sentiment analysis, which is bag of words and SVM plus, emoticons and emojis, so and a couple of dictionaries related to sentiment from Wikipedia as well as from SentiWordNet. SentiWordNet is a version of WordNet that has sentiment score for the words. Then we have emotion words all taken from SentiWordNet, we have emoticons, and we have average sentiment score, number of misspellings. This was computed by Microsoft Word spell checker. Don't be afraid that you can put everything in Microsoft Word for every user and check the spell checker. But this is a good one, so we used it. We call it from directly from operation system, so just overuse it because it's embedded in Windows itself. And then we use looking for some unknown words. Unknown words is those words that are never in dictionary, so we assume that this is this completely wrong word, or maybe this word is not spelled. And then we count the average number of terms. So for images, we extracted the image concepts. So every user, in our case, is represented as a distribution of image concepts. So every user has a fixed size of image concept distribution, which basically tells what this user usually posts about. And trained based on ImageNet, the actual model is Google Net neural net. So we run it on GPU, it's pretty fast. Those in school who really want to use GPU, let me know, I'll give you cloud server for that, okay? Really want to use. So all resources for you, just please come up with something nice. And then for the locations, we use a distribution among the venue categories and this kind of ability features related to areas of interest. Then further, we used the exercise types, number of accounts, the heart rate, the oxygen consumption, and we feed it in a Fourier transform, come up with a vector of 500, and this vector of 500 is basically a representation of user in terms of how they do activity in dynamics. So it's not just type of activity. It's, for example, how human body reacts on the slopes, how human body reacts on weather. We also consider weather information because we have it, and how they correlate between each other, different heart rate, for example, and speed, and so on and so on. So very important. Some of you can try a task of activity recognition here, because we have labels of all activities and we have raw data. Very, very sweet task for this summer school if you want. We didn't do that yet, so but data you already have. And then the summary is like this. All this multi-source data goes somewhere. I'll tell you later where it goes. To get something, I'll tell you later what something you want to get. Okay? Second part is also 1 hour. Any questions so far? Okay.
I have one question.
Yeah.
What is the number of terms which you discussed in the previous slide?
Number of words. Now we call terms those words that are already defined by synonyms. That's why they call terms and differentiate them from words, because all synonyms will become one term. That's because school education is based on old style of English. So seems like some time ago it was mutually replaceable, but nowadays lunch. So lunch is actually something around 4 o'clock. And dinner is something that is lunch, and then supper is something called dinner. Well, it's not related to this, but anyway, it is.
Why Russians use Old English?
standard of English, and then the system didn't really change. It changed recently, but I believe those who are going to school now, they maybe speak proper. But like my generation was taught as dinner and supper. So we're talking about the names of the meals here. Okay, so I hope your lunch, dinner, or whatever meal was nice. And yeah, you enjoyed Russian food here. I'm going to start with the second part. Second part is about applications. For those who are social scientists, I will be talking about sometimes not that straightforward things, complicated models to process the data. But if you go to some artificial intelligence conferences, like for example, this time I went to WWSSS in San Francisco. Several speakers from such companies as Google, Uber, and LinkedIn, they actually still use linear regression just a bit to do a RISE. The thing is, our data is very huge, and these models are very fast, and nobody cares if they're simple, if they work well. So everything I'll be presenting to you was created to be novel, not just in terms of results, but also in terms of the approach to data modeling. But however, all of these models have a root into something very simple. And this very simple is very easily accessible to all of you. And I believe most of the cases, the results wouldn't be too much different from what we achieve. I don't try to say that innovation in data modeling doesn't happen, but in general, if the family of models work well for some data, then even not the most sophisticated one will work well. So just if you want to work on a similar problem, look for similar models that you can apply, download from internet, write a Python script, and get the results straight away. When we will obtain the results, if results are good, then you can start model to improve it. That's how I do usually. I never start building models. I always look for some existing models, see how they work, and then work on further development to make it even better and tailor to the problem and so on. Okay? So, first, as you maybe understand from quotations, we will be talking about demographics. In particular about inference of the demographic attributes. And our demographics is different individual attributes such as our age, our gender, maybe some other related things. Well, the demography as a science, they divide differently what belong to demographics or not, but some basic attributes are always there. So we'll be focusing on the basic attributes of demographic. Basically, this is the first research on this multi-source learning from multimodal data for user profiling. So this is also first work in the field. And we released our first data set. So this guy, I mean, who knows this guy? Okay, at least we watch cartoons, it's good. So this guy, he's 40 years old. I checked Wikipedia, he's 40. And he's male. That one is more straightforward. And just by knowing these two things, we can dream of so many applications where just these two attributes could be very useful. And this is again a public application as well as business applications. Like if we look at these two attributes, we can say that similar people actually like to stay at home, they go to pubs, they maybe go for shopping, maybe they have families as well. By the way, those who know demographics much better than me, they can actually tell me more about this, what we can tell on these attributes. Anybody want to contribute? What we can tell about a person by knowing their age and gender? I know some archaeologists are very, very interested in this as well. So just by applying these two simple attributes, they already significantly can reduce the amount of financial resources that they allocate for advertisement, for marketing, just by being able of splitting just this simple interviews. So if we can infer this well, this is already a very good research and business idea. Those who will be working on business applications, you can think about it as well. Also some other attributes which are essential, maybe for certain field or so on. And of course you can verify as they're easy to produce. Then for wellness, these guys tend to have certain types of disease, so it's also useful to know. So these attributes also kind of belong to wellness category, because the same health status for different age may mean completely different things. Then you may advertise dear to him, which is not too interesting application just because it's for money. And then of course we can assist him. Maybe these people may tend to have some not very healthy habits, or may have certain needs, so we can help them build their recommended system to help these people to achieve their goals, support them in their life, and so on. So there are some research in this direction. So some works were doing demographic profiling, for example, PAN competitions. Anybody heard about them? I suggest you to look through this very enthusiastic group led by Professor Paolo Rosso and some others. We actually have collaboration with them. Next year I will be giving keynote in the next competition about multi-source data. So they actually started this thing in 2013, I believe. They were predicting gender and age of people based on the microblocks. And they already managed to get some nice results. So we later generalized it for the multiple data sources and get much better results, further better results compared to them. There were some other research was using data sensors. Some people were working in multi-source profiling, but they was not doing the user-generated data. It was using some attributes for people. So that was kind of a big extension of the patent petitions too. Oh yeah, by the way, Polo asked me to say that currently there is a pen on Russian language, so those who want to participate and predict gender of Russian people, you can easily find it. They just started maybe half a week ago, so who guys want to participate. And then they have some dimensional data sources, and some people will even try to do demographics from voice records and some handwritten applications. This one is already to speech processing and image processing, so it's not really related to us. Some others was doing the public profiling domains as well as the generic profiling for the country level, for example, based on some correlation analysis and so on. And some people was trying to infer physical attributes, for example, our daily activities like brushing teeth, sit-stand, and so on. That one was purely based on sensors. Usually they don't combine social media and physical data. Most of them are fixed on one specific data source. So our input was, well, if we have this multi-source data that describe people from so many different points of view, perspectives, and if we are able to find some ground truths to train the corresponding models, why don't we try to address the problem of user profiling from multi-source learning perspective? And we are hoping that multi-source data can help us to achieve much better results, and indeed it can, I will show you later. So I'll go straight away for model. If somebody is curious what is random forest or what is ensemble learning, this actually is a separate topic, and it's not what can be really covered in 1 week. But by understanding the principle how this model works, you can actually apply it by using Python or using some other platform like Knine and so on. You even don't need to do programming. There's a platform called Knine. So another one is called Vika. You can just drag, drop, and get the machine learning pipeline without any programming for those who want to do that. So the idea here was like that. Now you have a multiple random forests. Random forest is a set of decision trees. So idea here is like that. If we randomly generate many decision trees based on different data representation, different features. Every tree we pick up different features. In general, this kind of classifier will be balanced, and it will also automatically perform feature selection, so we wouldn't be too much bothered by a very high dimension of the data, which is our case. Because those weak trees that don't perform well, they will be eventually not be used. They will be used for classification, but they wouldn't be majority. Majority vote is basically the last step of random forest itself, and we also combine these multiple sources and also do voting in the end. So it's an ensemble of ensembles of classifiers. Why we make it ensemble of ensembles is because we have Twitter with a textual data modality, which is conventional NLP type of learning things. And we have Foursquare, and it's very hard to imagine that we can combine Twitter and Foursquare in one vector, and then these features walk together the same way. It will be a bit strange. They are, I cannot say they are incomparable, but it's difficult to combine them together because the nature of the data is very different. So for every block of modality of the data, we build independent random forest. And when we combine the results, we make a weighted voting for these models. So the model is pretty straightforward. Also, when we make a voting, we multiply it to the performance of the model, of the random forest on this data source. And also multiply it to some coefficients that we iteratively learn based on something called hill climbing, which is just make it faster than just you check all values, but it's not that smart one. So it's ensemble of ensemble, and we train this ensemble based on ground truth records. Ground truth records was a problem at the time because we get a nice data set from multiple data sources, and we happy to predict something. We don't know what to predict because we don't have any actual labels of a person. We were looking for maybe genders or ages, but Twitter doesn't provide it. No, they have gender but don't have age of people. And for us, age was essential because we always see a combination of the meaningful rather than just gender itself, just gender alone. So the idea comes very sudden. We discovered at that time that Foursquare API introduced the link to Facebook account for those users for those who connect. So we crawl Twitter, somebody posts Foursquare check-in inside Twitter, so we get their account, went back to Foursquare, and in their account check what is their Facebook profile, went to Facebook, and download all their profile. So we get multiple attributes of these guys. We get their age, gender, occupation, relationship status, and some other attributes. So it was very sweet. So we trained this model based on this kind of partially labeled data. For those who didn't mention their age, we actually infer their age from their education past. And we found that this is a very nice approach because it's a fluctuation in just maybe 2.5 years. So you wouldn't go beyond 5-year age group most of the time. So you can use these partially observed labels to train the models, and then the model can predict results for completely unobserved entities, like users who didn't mention anything about themselves. So far, is it clear how this works? This is something you can implement in a summer school. This is easy model. Okay, so it's ensemble of ensembles. And generally, I would say that ensemble learning approaches, they may be not so easy to publish in AI conferences, but they're extremely powerful. In fact, if you have many big classifiers and you manage to get nice heuristic ensemble that can combine these classifiers either by stacking which learns the ways of them or just voting, it very likely will be very strong baseline to whatever other fancy algorithm you create. Ensembles are very powerful. Just they are not so easy to be described and analyzed. That's why community not that widely, research community not that widely accept them. So these are some details. We also use some oversampling techniques, which is also very useful. Oversampling is when you apply, basically you create a copies of data records of those data records that belong to some rare classes. Like in this data set, age group 40 plus was relatively sparse compared to age group 20 to 30 or 10 to 20 years old. So we oversample those for 40 to 50, so the number of records 40 to 50 was kind of similar to the number of records of other age groups, so model wouldn't be biased towards certain age groups, and they also can detect those who are a bit older. Of course, a bit less accurate, but it's already much better. So, oversampling and other techniques, if those who do machine learning, I don't have any case in my, at least in my works, where just as simple oversampling as small didn't help. Always help. You like have some nice model, then you do oversample a bit increase always. Sometimes a lot, sometimes a bit, but never degrade the performance. So this is something you can use. And then we infer the number of trees for each random forest, infer the ways in which to combine, and start a random iteration of hill climbing. Hill climbing is when you randomly pick up some point, and then you try all the neighbors of this point. And if some neighbor can help to increase results, then you move to that direction. If they cannot increase results, then the algorithm stops. And if you restart this 1,000 times, you have a good chance to go to some global, well, not global, but at least reasonably good minimum or maximum, depending on what you're optimizing. So it's also another good heuristic can be used. You always apply it just because it's fast and it works reasonably well. And this is results. So here in results, you can first read a paper. It's a CMR paper 2015, you can find my webpage. What is interesting here? Look, here is single data sources. Location data source. Well, by data source I also mean modality. I flip the definitions basically. Location data source, WWSSS features I was talking before. Model trained only on heuristic features of text like number of mistakes in spellings. LDA features, the topics, and image concepts detected from Instagram by neural net image from ImageNet dataset. And you can see that they perform differently, and you can see that, for example, for gender detection, LDA on text performs the best among other modalities. And for age prediction, heuristic features like number of hashtags and misspellings perform the best. So for this task, the guys who decide to make a pancake petitions on demographic profiling, they were quite right. They empirically prove the same thing. So yeah, text is the most powerful modality. Yes?
What is the metric in the table? Accurate?
This is macro recall. Kind of, it's macro recall, so it means you compute recall for each age group and then divide by number of age groups, divide by 4. So if you have too few data samples, it wouldn't be unfair.
So you divide first into 8 groups?
Yeah, we have how many? 5 age groups.
4. Sorry.
4 age. Huh?
It says on the.
Yeah, we was using 5 initially. We made 40, 50, and 50 plus. But 50 plus was too few people. So we eventually combined 40 plus. This kind of age group. Yeah. And for this metric, if you just compute recall, I didn't put in slides, but if you just compute recall, age group 10 to 20 and 20 to 30 will be very accurate because it's the majority of these people. And another 2 age groups, 30, 40, 40 plus, much less samples, so model perform worse. So when you take the average of this metric, it eventually become a lower result. We recently managed to get this somewhere around 0.65, 0.7.
Why recall not accuracy?
Huh?
Why do you use recall not accuracy?
In this sense, it's kind of similar thing, right? So macro accuracy and macro recall is similar thing. Look how you compute macro recall, and you will see that they're kind of. In fact, in paper it's called macro accuracy, but I always call macro recall because nobody knows macro accuracy. Because accuracy already by itself matters. So well, we can discuss that. later. Okay, so then if you go to this double source combinations, you will see actually media, which is images, always top up compared to single source. Well, significantly top up, and it appears that the second priority of multi-source learning is the image data, because it's rich, and because if you go for the image by itself, you see that they actually perform quite strong compared to, for gender, for example, it takes the second place. It's almost the same as just text. So, which means that if you guys decide to do something related to maybe profiling, then it makes sense to look into the image data or maybe video data as the next step. And then maybe incorporate other data sources. Because for this task, image is very powerful. I'll show you another task, image not that powerful. That's why we need to read literature and think about potential models that can contribute to this particular task based on previous experiences, based on our own thinking. And then, yeah, multi-source data always performs the best compared to others, combined in a sample way. And also, it's important to notice here is these early fusion features. Early fusion, if you just combine all data sources together in one long vector, three random forest, so you can see results really bad. Which means multi-source learning is not about getting data, representing it well, and fitting in a model. It's about building a model that can work with multi-source data, because this data is very different in nature. If you go to image retrieval or image processing domain, very often early fusion will be the best option, because wherever features you extract, like I was talking in the beginning, they all will be kind of about the same thing. So they will work well together. But here, some modalities may have very low weight because they're not too useful for this. In that case, it's better Tat-Seng. That's why fusion doesn't work well here. That's harder. Now we try other classifiers. We tune SVMs, we tune MPIs, and in most of the cases, our ensemble also was better, which shows that this kind of family of algorithms works well for this task. Let's go over the paper itself in the link. And also, those who will be working with the WWSSS dataset, it's good to read this paper. It will take you maybe 1 hour. You'll understand the nature of the problem and the dataset itself much better. So it's always good to go for the original paper, because we describe quite comprehensive inside the paper, except for description that you were provided as a school participant. It's good to go for the paper. It's always a link there as well. This slide also available. Okay, so it was the first work. It combines multiple data sources with the profiling, and we propose our multi-source cross-region data set. So what is good about an USMSS data set is that it was crawled in 3 geographical regions. One was Singapore, another was London, third was New York. We also tried to crawl Melbourne, but there was not too much people who used Foursquare there, so we didn't include that part. So it means that for both computer scientists and social scientists, this data set, we can do very nice cross-region research. You already have data representations of people in one region. Words they use, topics they talk about, values they have. You go to another region and see how is it different. Is it really different? How much Singapore and New York are similar and different in terms of social media verification? And the next further step, computer science question could be, well, now we have a model trained based on Singapore. Will it do better in London or New York? Will it do well in other cities? Does this really affect machine learning? These kind of questions we didn't address yet, and it's really easy to address by using simplistic models. So in this school, some of you can try to study this. But again, guys, result number doesn't work. You have to explain why. It's very important for all data sets. Well, whether I talk about it, Sergey, or any other organizers and lecturers. Doesn't work, okay? You have to be a very good explanation. That's the whole purpose of this school. Okay? And then was another very recent work. This work is not published yet. This is under submission, and in fact, you are first who look into preliminary results of this work. You'll be working in a further modeling of this, but you already get some results, get some insights, and the most important thing that you guys have access to the data set as well. Okay, so you can have access to the data set about personality and multiple social network of these people. So you can see how differently different personalities behave in different social networks and how social networks correlate to each other and so forth. With one note, please, if you want to use it in your research after school, you need to collaborate with the author of the data set. I'm co-author in this work, but the first author is Ksenia Bura. She's one of the mentors. You need to work with her prior to further pursue this study, because it's very nice data, and of course, we want to contribute and see the results of this as well. Because we start in this new direction, so it's going to be the first work on personality for multi-source data as well. Okay? So, and data set name is news personality. So our inputs were like that. We have some demographic profiling results, and it's promising. It can take demographic attributes better based on social network. And then we also know that here is a mistake, should be personality profile. We know the personality profile in the previous work. In fact, in one of evaluation, kind evaluation 2015, we had a personality attribute, and it showed that personality can be predicted reasonably well. There are two scales. Which scales of personality do we have? Anybody know?
Gender?
Personality.
It depends on the classification that you use.
It doesn't?
It depends on the classification that you're using. I mean, the technique for profiling personality.
There are two most adopted classifications. One called Big Five, which doesn't have categories. It's grade your personality based on 5 scales. Another one would be MBTI. That one is discrete and it has 16 categories. So I will talk about it a bit later. We use the MBTI one because we get a nice data about MBTI. That's the reason why we use it, to be fair. So, and you know, personality actually affects everything. There are certain works recently come out. One is called Cambridge Analytics, and the project they try to do called Applied Magic Sauce. They claim they were helping Trump to win his campaign as well, but this one you can ask them. I don't know if it's true or not. The truth is that they can predict personality based on likes and social relations quite well. So they are our related work. Then another work is done by MBA and Watson. They also started this project recently. And Watson doing some demographics of personality. So personality always exists in all applications. And there are a few other companies and startups that they do personality profiling. They do it for text data most of them. One called Profiling from Italy. And I know a few more companies who do that. So it's very demanded attribute by research and by industry as well. So personality tells a lot about us. And for MBTI skill, it consists of 4 attributes. So when we combine these 4 attributes together, we get 16 categories of personality. One is extroversion and introversion. This one probably is the most famous. Then we have something sensing and intuition, thinking, feeling, and another one is judgment and perception. And each of them, well, they are related to each other, of course, but they are kind of distinct scales inside the personality, so they are supposed to broadly include all the cases of personalities. If there will be some psychologists here, they will definitely argue with me, because after we published our AAA paper last time, I get a few emails from psychologists saying, how come you do an MBTI but not Big Five? So, in case you guys have this question, I reply, we are computer scientists. We want to prove that personality can be inferred with good accuracy based on multiple social media data. We get some discrete attribute which is definitely related to personality. And we predict it. And we evaluate ourselves based on this attribute. Does the attribute itself correct or not? That's already another field. It's not we're supposed to discuss. We just can testify that as many psychological papers who claim that MBTI is good. So let them argue between themselves rather than the law passengers. We just play with it, and you guys, if you have strong feelings about Big 5 MBTI, you maybe can propose your own Big 5 data set. I think they can even have something, but our data set use personalities in MBTI. Okay? So we actually did 2 experiments. First experiment, I didn't mention, we also wanted to check whether it's possible to improve the personality profiling by integrating the temporal aspect of the data. If we learn from data temporality, can we do better predictions as compared to just multi-source learning? So with both multi-source and temporal model. So first experiment was devoted to this. Basically, we were thinking, can we put some temporal aspect into the model? So, and then what will be the window size? The window size of the temporal samples that we feed into the model will be optimal in terms of prediction results. So how many of you heard about recurrent neural networks? The recurrent neural networks. Okay, can somebody tell me what's the difference between recurrent neural networks and long short-term memory neural networks? Okay, yeah, somebody you can tell, right?
The essence of short-term memory network is to deal with this problem of vanishing gradient, which appears in OA elements.
Yeah, correct. So the problem of vanishing gradient is basically when we do optimization, right? We do something called backpropagation. Backpropagation is basically taking a gradient and the layers in neural networks and recurrent neural networks. They are the time points, basically. So we took a snapshot of time points and feed in these multiple layers and do backpropagation. So vanishing gradient, the problem is that the gradient becomes too little. It doesn't affect the optimization at all. In case if you just simple neural networks, it's just a stacked neural network layers in time. So they propose something called long short-term memory network that contains 2 words, long and short-term memory. And basically what these networks can do is forget. This network randomly forgets some pieces of what it learned, so that the problem of vanishing gradient can be eliminated. Go Wikipedia, everything written very nicely. Also can download the Keras or TensorFlow libraries and randomly within the CPU get use of recurrent neural networks. Really few lines of Python code. Can be one of your projects here as well, if you're curious. Just explain me why neural networks and recurrent neural networks work well for this task, and then it will be useful. So we use them here. We use LSTMs. And in the first experiment, we was basically checking how do LSTMs can help us leverage the temporal component of the data, multi-source data. And the second experiment was now we take the best model from the first experiment and see if we take out some data sources from it. Will it decrease or increase the performance? Will multi-source learning benefit to this work? So 2 research questions. Does that temporal component help? Second research question, does multi-source learning make sense for this kind of research? Okay? So basically, just another problem here that many data is missing. And this one you will meet in all data sets that you guys have, because people, they not always participate in non-social networks. Some of them will have only 2, most of them will have at least 2. Some of them have only 2, some have 3, some have 4. The different data sets are different. So if you want to do machine learning on these things, you need to find some data completion technique to complete this data, or can propose a model that can deal with incomplete data. So in this work, we used non-negative matrix factorization, data completing techniques, which is based on matrix factorization, so you can understand from the name. H is a representation of a matrix of factors, and then version it back so it will complete the missing data points. You can read in Wikipedia how to use it, and there's multiple libraries that implement it. You can use it even other data computed techniques, like take an average of the column and put there, or take the most common value, or take a mean, so on and so on and so on. They actually work quite well. Even sometimes you put zeros everywhere, still work well. So, but it's for machine learning. For qualitative research, doesn't really make sense to compute any data because you confuse yourself comparing this. So this again, must be careful. Okay, so we have multiple endpoints. We have LSTM network. This is example of LSTM network consists of 2 layers. Basically, this is a structure, and it will be one forget gate and one data gate and so on. So you sigmoid, you get probability, with this probability, the network will forget this piece of data. And another time it wouldn't forget. So it will look kind of like human. So forget something and generalize better. And the problem of vanishing gradient will be solved as well. We can discuss more about the theories. Yeah, so we feed in a maximum 10 times periods and use non-negative matrix factorization. So we use 3 social networks, and these social networks were completed by non-negative matrix factorization. Now we have to complete data, so we don't need to deal with missing data, we don't need to use frequency data modeling for the thing. This is results for the 10 windows. So you can see that these 6 intervals and 7 intervals are generally work better for most of the attributes. So this is about 1.5 years of data. So it means if you have a data about somebody's personality for 3 years or for 2 years, using whole data would not be as helpful as using some part of this data. Which is again interesting. Sometimes people say, well, more data will actually not. In this case, fewer data doesn't really work, more or less uniform, then become really bad and C7 and then become worse again. So maybe something happened. Maybe it was some world event. Maybe we have need some additional sources to explain that. Or maybe some psychologists can tell us that actually some attributes of personality they change reflects the external world, or maybe they just change themselves. Maybe others don't change, that's why some of the attributes are quite plain. So this is the interesting result. And here are the results for every label. So this is one label, another label, third label, fourth label. This, for example, is erosion and revolution. So you can see that for SN, TF, and GP labels, LSTM with 7 times frames and with 6 times frames was the best among other methods. We also tried gradient boosting, we also tried SVMs, we also tried some other temporal models. LSTMs were working better than that. However, for extraversion and introversion, gradient boosting, training on all data, was the best. We think that extraversion and introversion is this kind of attribute that actually is not affected by time. It's something constant in your personality, so it doesn't change much. That's why varying type of the data doesn't affect anything. And gradient boosting is also assembled in models. So it's one of these examples when fancy models, neural networks can perform bias samples, which are always strong. Other baselines, where we just feed all the data with very long vector, which is early fusions, always much lower accuracy. I didn't put it in a table here, but you can read it in a paper that will be published. Here we presented the first work on personality detection for multiple social networks, considering the temporal component. Hope to get it in a single this year. Some additional analysis also in the paper, so I didn't address it here. So these 2 attributes are something related to our identity, like our gender, age, personality, something inside us, and this is reflected in social media, reflected in the way we communicate. And it's reasonable to use social media data to predict these attributes. But how about try to predict related to our health, to our physical conditions from social media. This part is quite often questioned by researchers, and we will start in this research direction on involving the sensor data. Many of my friends actually was doubting that any meaningful results, any higher than random results can be obtained, because it seems unreasonable to use pictures to predict somebody's weight if these pictures are taken by this person or something else. And many of these kind of arguments was about that. So I'm going to present to you the first work on integration of physical data, which is sensor hardware and GPS, together with social media data for user profiling. And this is already another data set called the newest sensor. It has sensor data and all the other social networks related to the sensor data. So you can either work just on sensor data, just on social media, or combine them together if you find very nice application or topics for research. Again, if you want to have your own topic, there's no problem. In fact, we encourage that, because those who sit in these fields, we are all biased, because we already tuned to certain way of directions we used to work to. But you guys, maybe you see it the first time, you can find something very, very, very different. Like one of the research projects I was just discussing with somebody from here. They proposed a very interesting topic, and I didn't think about the topic before, so maybe the person can share with you later in the presentation or something. So we are looking for that results. So we're talking about usual balanced user profile. And because of this common problem, people, they are not really aware of their lifestyle, and they tend to soften their own impression about themselves, so they keep living like that. And this 40 years old guy should be very healthy. It's based on cartoon. I have to watch whole cartoon to verify this, otherwise I cannot make this assumption. Yes. Just obesity, it causes so many chronic diseases. It's different type of cancers, it's hypertension, hyper pressure, it's type 2 diabetes. Type 1 will be different, but type 2 is often because of overweight and high blood sugar constantly. And then they have arthritis, and some mental illness and depression. Actually, understandable why, because society nowadays not always accept people who have any problems. So people feel not well. And this kind of heavy weight is very difficult for people to live with. So that's why we think we can make some app or watch or Benson algorithm that can integrate all your social networks inside, and based on this make suggestions to you regarding your lifestyle. Like, hey, you posted picture of hamburger yesterday on Facebook, or like, seems like you don't move enough, or you are going to the wrong websites or something like this. You better take care of your lifestyle. If Apple Watch can leverage this kind of data together with sensor data and can give meaningful recommendation, it will be a very nice application. So we decided to address this issue, and our inputs were, we already tried individual profiling for personality and for age and gender. We really know how to get data from wearable sensors, and sensor data obviously very related to our health. Otherwise, it doesn't make sense to wear with them, and it doesn't make sense all the businesses they do on these sensor devices. So why don't we try to combine social media and sensor data together and try to get some meaningful results in terms of machine learning. And also some part I'll show you some at least qualitative description, qualitative description of these results. And again, we're working with multimodal data. We work with images, with text, with locations and sensors together, and even better around. So the idea was like this: we have social networks, we put activity types, and then we want to predict two things: the fluctuation, which we call BMI trend, will the weight increase or decrease, and BMI itself, which is 8 categories. Here is 6 categories, because slide is not wide enough. Actually, they have many categorization. We was using the 8 one, but this one is the 6 categories. categorization. Basically, the range is the same, no difference. It's different medical association with different categorizations. And just here, you may ask, how do you compute fluctuation? So we monitor social media users continuously, whether they will change their weight value in their page or not. For those who didn't change their value, we cannot definitely say that these people didn't increase their value or decrease or keep the same. They may just don't want to change because they get slimmer or fatter and they don't like it. So we only include those users who changed their weight during the crawling process. So we know that they manually label their own weight, and we know their height, so we can compute BMI change. And those who didn't do anything, we just don't treat them. While for the BMI task, we just go to all those who have height and weight in their pages, so we can compute their BMI. So in the model, they don't release BMI itself. They release height, weight, and then BMI can be computed by us. They also have age and gender labels, so it's also included in data set you guys want to use. You can try to predict gender and age based on sensor, purely sensor or sensor social media, or you can see how it is related to different types of data. How your gender and age related to how you do exercise, or also what pictures you take, for example. Okay? I will read slides, it's no problem. So, just a bit background, there's something called multitask learning. Anybody heard about multitask learning? Oh, good. So what is multitask learning?
No, I never heard. Just physical use.
Oh, you want to show that you didn't heard. Oh. Okay, whatever. So, well, how many of you heard about regression? Or how regression works? Do you know? Roughly.
Putting a line through it.
Fitting a line, right? So if you write it in the matrix form, it will be wx minus y, right? It will be also normal parameters, so basically summation of all the members of this abstraction. And multitask learning is when we say, okay, now we take one regression related to one problem, and then we take another regression related to some should be related to the first problem, and then we take many of them, and each of them we call task. And now, inside the formula, inside the objective function, we define a rule that connects the learning procedures of these regressions. And basically, you do joint regularization. You manipulate with all w's within one norm rather than you take them separately. Then they will affect each other, so you can learn some information about the one task, for example, gender prediction, by utilizing experience of another task, for example, age prediction. Assuming that age and gender are related, because if they are totally not related, then it may spoil the results, but maybe just train them separately. So there's a difference between first model where we train ensembles separately and this model where we train them jointly. There is a library called Malstar. This library written for MATLAB. If somebody knows MATLAB and like MATLAB, you can apply this multi-task learning on your data sets. They are quite powerful models. For those who don't like MATLAB, there are some Python libraries for multitask learning, so you can always find. So as long as you know how does the family of the models called multitask learning, you can find nice. And these models, they are good for multi-source data because data sources are related to each other. Just we don't know how. So we let the model learn it how they're related to each other. We don't need to bother about it. So we eliminate all heuristics and we just let the model decide and understand what is the relation. Another approach is neural networks. We also can do this quite well. So this is basically the idea. So we have one data source, we have the data sources, right? It's Twitter, Instagram, Story, and Amazon. Each of them is some representation of the data. And you have different groups of users. For example, this guy contributed to these two and to the last one. This guy contributed to first and the last two, and this guy contributed to all. And can be also some tasks related to only one data source. So it's all combinations and permutations of four. In this particular case, you don't have cases when we have only one source, we always have two, because we crawl data, as I explained before. We always have filter and something else, otherwise these guys are not in our dataset because they are no longer multi-source. An idea here like that. Now let's define tasks as a combination of data source. So these guys is one task, these guys is another task, these guys are so that label is always the same. A combination of data sources is our tasks. And then we learn these tasks together so that we don't need to complete data at all. We kind of train K models, each of them correspond to different combination, and then we put some regularization inside the formula, I'll show you later, that help them to learn each other. It will be adjusted to each other. Particularly if one task selected some feature by applying L1 norm, which is for feature selection. Like this. Then another task most likely also selects this feature if the task consists this data source. So the selection of data sources will be consistent among all tasks. So in this way tasks affect each other, jointly learn from multiple social networks. Very powerful approach, and I believe can be applied to many issues. I can give you source code, but in MATLAB, sorry. I had to use MATLAB as well at that moment because I started from some pre-existing models and then I just implement our solution based on some previous models. So this is just notations. So basically this is an objective function. This is logistics or least square rows loss. So can you tell me what's the difference between logistic and least square rows, and for which cases we use one, which cases we use another one?
No linear function.
Again?
Logistic distribution is one linear function basically, and then otherwise linear function.
Both of them considered linear actually, because if you go to logistic, you will see that this mapping in the top is still linear.
Yes, if you take the log form, they can be linear functions. So basically, if you use the general logistic function, you can interpret the magnitude. So we need to use other way around.
Basically, there is some research saying that they're kind of similar to each other. Just one of them output something, some value, and another one output the probability. Yes?
The continuous value prediction is linear, categorical value prediction, discrete value prediction.
Yeah. Okay, so this is our logistic loss, and we have two regularizers. First regularizer is L2-1 norm, which is a summation of L2 norms. That's why it's 2-1. We have many L2 norms that are summed together to become L1 norm on top of the L2 norms. And this, this corresponds to what? Why do we need this kind of regularization? How L1 norms help in regression? Why do people use L1 norms? For feature selection, L1 norm is very good in reducing the weights to something very low, to 0. While the L2 norm makes it very smooth, so weights will be still somewhere high, but the norm is very strict. Just in a few iterations of gradient descent will put the weights to 0, which will be a feature selection, natural feature selection. And here we perform feature selection jointly. So if this source exists here and exists here, then these two guys will be under this summation, because the summation of sources and features that are in one source. And they will be doing joint feature selection. That's how sources affect each other. Except for that, we also say that categories, the BMI categories that are close to each other, for example, super fat and just super fat, they may have similar weights, right? Because we assume that social media behavior is similar. So in this regularizer, we say, okay, then we take consequent categories and subtract their weights and try to minimize the difference so that the neighbor categories will be having similar weights. And since all of them are neighbor to each other, so they sequentially affect each other, so they will smooth the learned weights over the categories. So we have smoothing regularization as well as feature selection regularization, and we learn and join it together, so we can get these results. you can see that, that for BMI prediction results are not high at all. These results are again in the form of macro measure. So if you go to some categories like normal, like fat, and like slim, like as tripotic categories, then the results will be quite good. It will be 0.8 for precision of measure, 0.7, that kind of thing. But when you average some of those very fine grain categories like super fat and fat or super slim and slim, seems like people behave similar actually. So we can quite often confuse them between each other, and we sometimes don't really predict them correctly. So here it lies I didn't put, but if you go to my PhD thesis, then I have chapter about kappa statistics about this work. And weighted kappa shows that actually if we penalize those misclassifications that are far away and not penalize that much those that are close, actually results much higher. So if we divide into not so fine grained categories like 3 categories, actually the model can work quite well. And anyway, regardless of the results, you can see that just textual data performs the best among others. Then when we combine sensor data and text, it performs the best among other combinations, not as mobility one, we get the same result. And here it makes sense, right? If you want to predict some physical attributes, it makes sense to combine sensor and the best predictor from the previous result. And then if you get 3 source combinations, then sensors, many semantics and visual features you'll get the first result. This is very interesting finding because text disappears. Become more sources and actually text become not that good compared to others. Well, difference is about 2.5%. And then multi-source learning again performs the best. So it's already 3 times and telling you the same thing. In 3 different works and 3 different tasks, different data, but still the same thing. So I'm very convinced about that. And this is BMI trend prediction. Here results much better. You can see that for BMI trend prediction, the 0.718 measure can be achieved. So this is already quite promising. It means we can quite often say correctly will the weight of person increase or decrease based on his social media activity and sensor data. And of course in training test set, not all of them have all data sources. Some of them have 1, some of them have 2, some of them have 3, some of them have 4. Which means based on what we do in social network, actually can say, will our weight increase or decrease? I say weight because height doesn't change. Yeah, so this is very promising results. And we recently get a bit higher number here, so we are looking for other models. In particular, we use convolutional neural nets to perceive this situation. I also have some collaborators from South California University. They're working on this data sets. So we hope to get some good papers on details and well in the future. So all of you are very welcome. This is release data, so we can work together on this data after school, or you can try to work on it by yourself as well. Just download from the web page. Yeah.
I have a question. Why when we mix up 3 data sources, the text drop? Is there like a reason for that?
We must again.
When we collected 3 data sources, sensors, video, semantics, and visual, why the text wasn't there? Like, what makes it not good for 3 data sources?
Why we don't have text here?
Yeah. Why it's good when it's only 2 data sources and it's not? Is this when it's 3 data sources?
That's a very interesting question. Well, so we explain it in a way that textual data actually have a much lower dimension compared to visual data. Visual data is a vector of 1000 for each user.
isn't sensors data should be also lower dimension compared to visual
Sensor
data?
is about 600, 700 because it can Fourier transform, can send the spectrum mix for all the different conditions. And when you semantics and mobility, it's also high dimension because it's 764 for square categories. While text is kind of different from them. So we think that in terms of model, that could be a reason and this is a problem. Because it means model cannot handle this kind of situation well. They throw away the low dimension features, which is must be worked on.
Why is the two case source data like sensors is a high dimensional data source and text is a low dimensional? Why it works together?
Somehow visual data affects that. And if you go to results, you can see that the difference between that one that has text and that one that doesn't have text is just 1.5%. So, well, if it's too different, then it's a big trouble. And since difference is not that huge, need to be investigated further. In fact, you can try to open this. I can give you a model and you can try to understand what the reason is. Our assumption was due to dimensionality, but that could be wrong. We didn't verify this. We need to be further studied from machine learning data mining perspective. Yeah, so here we combine sensors also media data and we combine different data sources and we release the very first data set that have both social media and sensor data together in one pattern. So it's very good. I think I need to be a bit faster because we already close. Aleksandr, sorry, we have teamwork from 4:30. Well, anyway, you guys have a teamwork Thursday, so we are very excited, right? Anyway, I think already all of you fill up the form, right? We agreed to fill up until the end of my second lecture. Still have some time a bit. Yeah, so the problem. Yeah. I know. I'm supposed to finish 4 o'clock.
Yeah, at the beginning at 4:30, the team will start at 4:30.
And I think Sergey would like to introduce the data set as well. Okay. So, we talk about individual user profile. We talk about the difference of individual user attributes, but we didn't talk about the groups of users. Yeah, the groups are very important because group behavior people affect the one group, they affect each other a lot. Groups of people also very important for marketing and advertising as well because when they do customer studies, they want to know what types of groups they have inside there. What is the unique characteristics of this group so they can address them and further boost their whatever they want to boost. Same as in research. So what's user community? Is some way of splitting people based on some parameters. Can actually whatever community as much as it makes sense. So this is a community of individual people. Yeah. And from another point of view, these communities can be split in different way based on the location mobility preference. So maybe this group may be staying in a region called Jurong West in Singapore, and they like housing. And these guys, in Singapore, this one is a super party island. Everybody goes there for drinking and for parties and for everything. So maybe these guys need more facilities there of a certain type. And use facility supply. So communities can be very diverse, very different, but how we define our task. So very different things to them. And maybe it can be in terms of purchase. So some people they like sneakers, and another one may like chicken rice. Chicken rice is a very popular dish in Singapore. So the first time I prepared the slides, I was making that for Singaporeans. Some nice examples. Basically, it's rice with chicken and with some special sauce. Actually quite tasty. Kind of one is this. Oh, and I think in China we also have it. somebody was from China. Yeah, and so then we know their preferences, we can market these goods in the social media platforms for them. So our input was, okay, social media profiling from multiple sources for individual people, for individual users is doable and it's always improve the performance. So how about the group profiling, community detection and clustering? So we are addressing this issue, and there's a couple of research works related to multi-source training, to multi-source clustering. Not too many works was done on integrating data sources from multiple social networks or multiple modalities. And none works was considering different ways of these modalities. I'll be going a bit faster for this presentation. Those who want to discuss further, we meet after the talk. So, how to represent user communities? Basically in the form of a graph. So we have a graph. Inside this graph we have some type components, so it's a highly connected component, so it will be a user community. One common way to define this problem is a link-up problem. We have a right-cut reformulation, and basically they're similar. Basically we're trying to minimize people within community and minimize the inter-community link and maximize the tightness inside community. So this problem can be solved by something called spectral clustering. How many of you know spectral clustering? Yeah. You know spectral clustering? We didn't know it was called. Yeah, but how many of you know the PCA or something? Principal component analysis. Yeah, so spectral clustering is kind of, you apply PCA your data, get some orthogonal representation of the data, and after that you cluster it by k-means. Of course it's not exactly like this, but the idea is like this. So you need to get some good latent representation of all your features, and then eventually you perform clustering. Spectral clustering available in all possible packages, you guys can use it, and it's a very powerful approach. Even the simple spectral clustering is very nice. I would highly recommend it. So, but in our case we have something called multi-layer graph. It means the vertices users are the same, but connections between them are different. Different social networks are connected differently. Instagram in one way, and Foursquare another way, and Twitter could be not connected at all, right? Sounds familiar. So we have one graph, and so one set of vertices and different set of edges. But now we need to measure the distance between these layers, because if we can compare these layers, we can say how far they are from each other, so we can optimize our objective function. So we have addressed to Grassmann manifolds in exact formulation given in DOM 2014. So we define the distance between two layers in this way. We'll plug in this inside the conventional spectral clustering objective. So now we have conventional spectral clustering basically is a so-called trace minimization problem. So we minimize trace of this, which is something you want to learn, times Laplacian times the same thing that you want to learn. So this minimize this and first applying k-means clustering, we can get the good approximation of solution of the min-cut problem that I was talking about earlier. And if you plug in this distance that I just introduced in the previous slide here, we can actually get this objective, which consists of standard trace minimization problem plus this regularizer, which say, well, now give us the latent representation, the final clustering space, which is close enough to all other layers. So that's why we have summation of all our layers here. And then if you rearrange this formula, you can get something called L mod, modify Laplacian, and the whole thing will be again standard trace minimization problem. So by Rayleigh-Rais theorem, if you take again decomposition of this of the Laplacian, this modified Laplacian, you eventually can get a space clustering which will be solution of the min-cut problem. theories like this, but actually if you go read about spectral clustering in the web, you will understand it very well, and you don't really need to know this kind of fancy stuff. Or you can read the paper if you are more interested. This one published in CIGAR 2017, so I'll be presenting this in August in Japan. But it's already available online and in my webpage in academia also. Yeah, and then another problem is we we want every layer be consistent with each other. We don't want treat histogram and Foursquare and Twitter in the same way. We want them be multiplied on something so that if these two layers are not related to each other well, their coefficient will be lower. This coefficient double IG. And if they're related very well to each other, then it will be higher. So we will adjust the inter-source relatedness of them. To understand this, actually need to read the paper where we have all these formulas telling how to get one thing from another. But the main thing is that by rearranging this, you can get modified Laplacian cap for each layer. That is again trace minimization problem, so we can do decomposition of it, and then we can get the optimal solution. For multi-source, there is any problem. For multi-source clustering, this considering the weight of the sources. So those who are interested in clustering from multiple sources, and they want to treat one source differently from another source, is directly applicable. Not necessarily social networks, can be whatever sources. And this model is very generic and very nice model. I suggest you to use it. You can get a call from us.
And U represents which values? Like U is a matrix, right? U is a matrix.
Yeah.
It represents which value? Like contains the weights or...
Yeah, we learned it is the weights. And we have latent U for everything. And we also have U for each layer. So we learn U for each layer first, and plug them together, measure distance between each layer and the latent representation to get the final U.
If the graph is undirected, U should be adjacency matrix?
Yeah. No, it's not. Not of the
never be an adjacency matrix?
You have to. U will be a matrix of eigenvectors. You have to perform eigen decomposition of it. It's a matrix of some latent space in which clustering in a mutually consistent way on multiple sources will be performed in a proper way. So we will treat all data sources well, considering their correlation between each other, plus considering their relation to the final latent representation. Adjacency matrix actually involved in L in Laplacian computation. You can read about all this Laplacian matrix in spectral clustering. You will see how to compute this. No, it's not. It's not adjacency. Yeah, and then we get this weight, and this is the only thing we don't know yet, because we don't know how social networks relate to each other. So we propose a heuristic. We perform spectral clustering on each layer, each social network separately, and then see how much results of clustering are similar to each other. If results of two spectral clustering applied to different layers are similar, then this will have a higher weight. If it's less similar, it will be different, it will have overweight, and we summarize it from K for number of clusters from 2 to 100. So the average is supposed to be general value. So you'll get a matrix where we have three social networks and their corresponding relation to each other, which will be plugged inside here. And then the overall matrix can be learned. And it doesn't affect optimization because it's a constant at that point. So it's still standard trace minimization problem. And how to test it? We get some communities, but well, we can use some modularity metrics, for example, which is applied in community detection, but it's very hard to judge the modularity value in other this kind of metric because we don't really know what the actual modularity has to be for this particular graph. So in our works, we usually perform the so-called indirect evaluation, where we pick up some other application recommendation. And we plug in our algorithm inside there and see if this algorithm will be better or not. If it's better, we say indirectly, since it's a proof recommendation, it makes sense of good communities. The idea here is like this. We have some history of user. This history is visits of venues, of certain venues, in particular venue categories. Restaurant and cafe and so on in the past. And we have also the visits of his community, the distribution of places where people of his community go. Community detected by the multi-layer spectral clustering before. So we combine this individual and group component, sort them, rerun and get the final recommendation, where these two are parameters. So we can find individual. So we can put individual and group component, and we can get the recommendation results, which computed in terms of average precision P and DCGP. And you can get that in all the cases, either the complete multi-source clustering outperforms all other baselines, some strong baselines like CD++ and factorization machines, actually quite difficult to outperform, but in this case it will work much better. Except one case, which is New York case. You can see the red line that just popularity of check-ins of this person worked better than combination with any community popularity for this person. And the reason here is that New York, the amount of Foursquare check-in data is so huge, so by just using your past over the long time, this will help you to predict where you go in the future better than if you do collaborative filtering among your community of users. And this is a good example of by having data, you don't need any complicated model. Basically, simple e-commerce platform also works in this way. Just take all your past and see what our e-commerce probably not, because you wouldn't be buy some old things, but like this recommendation of a venue to go take your past, see where you go, and just do the same thing. Maybe at the same time, but nearby. In New York, it works better. In other cities, in all other metrics, the combination of individual and group component, where group component depends on multi-source data, works better. So this is indirect correlation to this approach. I highlight some of them. And here we have again combination of data sources and single source. And you can see the single source performs the worst, where Foursquare is the best performing data source, which is very reasonable because we are in a target recommendation domain. We recommend venue categories, and we train on venue categories alone, and of course it's better than just train based on text. However, you can see that just text Twitter alone, just Instagram alone should become quite high. And this is already a potential solution of a cold start problem, because even don't have data in Foursquare, just by using your Twitter and your Instagram, or just Twitter or just Instagram, you actually can perform recommendation where to go in Foursquare. It's a good example of cross data source solution.
They're actually all very close, just for a single model. For single models, they're very close, single source.
Yeah, they're close to each other, which is actually good, because many people don't believe that you can recommend locations based on images solely, for example, or so on. Because it seems like what we take picture about doesn't really relate to which pub you will go after 1 hour, but it's actually related and can be done. So it's very sweet results. And multiple data sources perform the best. In one city in Singapore, Foursquare Instagram is the best, or in London and New York, Twitter for Foursquare is the best. Twitter in Singapore actually not that well. In Indonesia it's very popular. In Singapore is so. So maybe it's due to the amount of data we have available. And this is a good result. This is a matrix of relational data source. So they are kind of similar to each other, but if you normalize it and scale, we can get quite different constant for relational data association between each other. So this matrix can be plugged in any other computation. Basically, it says how much Twitter similar to Foursquare, to Instagram, to temporal data and to mobility data in terms of spectral clustering. And we propose a new generic model for spectral clustering for multi-source. And we also propose to unite group and individual components for recommendation purposes. as I told before, data is not just about the data, so we need to apply it to somewhere. That's why we developed, with our development team, we developed a platform called bBridge.net. Actually, you can go to demo.bBridge.net and see the demonstration of this platform. The point of platform is integrate all the technology we see so far for some business use. And this is next up after social listening. It's already called social discovery services. This is a stack of technologies we use, and I just hopefully I can play a video for you, so you can see the use case. So we can log into the platform. This is a map of Singapore because we look for Singapore data, but it doesn't really matter. So you can set up very interesting multiple queries. For example, we are looking for 25 to 34 years old. These people must have college education. At the same time, the income level should be high. And for example, these people may like, let's put something from images. Should have cats in their images that they post. And then you can look for these people and see actually the distribution of these people among different categories. And pictures they post actually have pictures on actually have cats on them. So you can see here on the left side we have the distribution of these people among different demographic categories, among gender, age. I think I already go a bit further. Okay, sorry. Yeah. So you can see the distribution of this query among different topics, among different keywords, among different image concepts. So you can say, okay, these people also take pictures of people, of dogs, of skies, of tables, of sink, and a bowl, and so on. So we can see actually what is in the pictures of these people. We can see which places it goes in most. Like for example, this particular query goes to animal shelters and nightclubs. And we can see who these people are. We see the gender distribution, age, education level, sentiment, income level, relation, status distribution. So now you have a brand, like you have Web Science Trust. You can plug it in and you see who these people who are interested in Web Science Trust, where in city maps they go, what they take their pictures, what they talk about their topics, which places they go, what are their actual posts, and who these people are. And you can address them, so you can study social media atmosphere of your system very well. So this is very nice. And in just example, you can see that we can actually detect all these individual attributes for this particular post. So you can see that we detect the person, detect the cat in the person's hands, which is object detection, which is also available in our API. You guys can do it by yourself by using our API tomorrow or today, no problem. And then we have the actual text, and then we see this person, posted picture. She's 35 to 40 years old, the person who posted the picture, not the person on the picture. Then this is a male person. And this income of this person is second level out of 4. He is single, and his sentiment is, you can see, okay, neutral sentiment. Yeah, and he is also interested in the medical topics. So this kind of social discovery queries can be done for various topics, and yeah, I can give you the access to this platform as well if you're interested. So then, if we go further, we can see another thing called bBridge API that we also developed. This API was used to detect the Trump's marital status by somebody else. Yeah, so this API basically provides all these capabilities to research institutions and also to business users. So for those who want to utilize it for their business, they can just connect to our API, and now they can even do it for free because we got a company research, so we can do it. Yeah, and API includes user profiling capabilities, so given the text and images and everything, we can detect all the attributes of this person, as well as we can detect objects and images, as well as we can do some simple NLP capabilities. So it works in this way. So we can go inside this API, and for example, you want to perform perform some user profiling request. So this is the data that the person posted in a social media resource somewhere. So you can make a request through the RESTful API, you have SDKs as well. And then you say that you want to detect gender and age group, for example, for this person. And we put some additional text inside, like this is the person who posted something on social media platform. So on the bottom, we also can see the URLs of the images of this person. So it's a multi-source learning model. It's one of those models that was modified version of it was proposed in the previous talks that I introduced to you. Yeah. And you want to post, for example, one more image here. And we can take any random image from Google, basically. So this image can be, for example, the image of, I don't know, the image of, yeah, for example, image of flower. So the person who posted flower in social media and then text that you see. So we take a link of this flower, go back to our API. This site is really just for demonstration. It's in fact just RESTful requests. And we can get that this person is age 20 to 34 as a female. And we didn't have this information on social media. We predicted based on what this person posts. So we can be done in the millions of people on a very large scale. Which is very nice, and it's all based on public data, so there's no any problem with that. And we can predict more attributes, so we can see the relation status, village group, occupation, business finance, second level of account, education level school, the previous education level already obtained, and female user. And then we can go to other API nodes. So another API node is object detection, for example. The text was inside this request, inside this image that is posted as URL request for. So we can go for some other, for example, what we go for dogs. Yeah, put a picture of the dog in the URL on it, and then we plug it in inside. And look, you have all these data sets, you have URLs, or maybe you have some your own pictures. We can actually use this kind of APIs to get a full representation of what is on your pictures. This version of API is a beta version, so we will try to make it workable for all of you, those who are interested. You see the detected dog, detected the ball, detected the ground behind that. And you can do the same for so-called conceptually, which is more fine-grained sound categories. It's basically image and concepts. And that one, yeah, we say we want to detect 5 concepts, we will be doing the picture of color ability. And then, except for that, we also have NLP capabilities, and NLP capabilities are available in Chinese and in English. So we're thinking to do also some Southeast Asia language as well as Russian language to make it more comprehensive. So this type of AP is not available in the market yet, so they all do based on single modalities. So we're happy to announce the first version, and we have a paper in ACM Multimedia last year about the social discovery platform bBridge as well as the API. So we also get a publication and demo track last year. And assuming to save time, I will be showing you all the capabilities, but you can see this based on car, detect racing car, racer, some wheel, so very fine-grained concepts from the image. You can know what is in the image by just making this kind of calls without looking at the image itself. So this is a very nice application, and this is one of the recent things that we achieved. So we proposed a social media analytics platform as well as API for its usage. It can be used by others. I actually hope to get a Blackboard, but you already know how to use this Blackboard. I'm not quite sure. No. Yeah, I was trying to use it, doesn't really work, so probably I just put the credentials to you in the end of the lecture. Yeah, I'm going to finish soon. Here, some more inspiration for you guys. I go very fast because you actually can get slides and find much more than I will tell you. Look, this is distributions of correlation of different data sources to wellness attributes. And you can actually see that if you take the BMI into consideration, the skirts, the gowns, and what is this? Yeah, overskirt, and another Gauss, Gauss, yeah, are negatively correlated to BMI, which means higher BMI, less likely you will see gowns and skirts in the pictures. This is so nice to see this kind of correlation because it's really completely multimodal and multi-source data, but it tells us something maybe we know from a real life. And all these plots are available in my ICM Toys paper this year. You can download from academia, it will be maybe available a bit later. And then we go further, and we can see that, for example, cereal grades and pasta and number of misspellings is negatively correlated to BMI, which means higher BMI, less mistakes due to grammatical mistakes. As well as if you have higher BMI, less likely you will be eating cereal on your breakfast and so on that you're taking from your pictures. I really don't want to comment too much about this because I believe all social scientists here can explain much better than me. I just want to show you this, and now paper will still give some explanation, of course. But I would be very happy if somebody will decide to work on these flaws, on these results, or will go by yourself and explain me what are these correlations mean, what is a social science, psychology maybe, or other theories behind that, what is it related to self-perception or to something else. And we have multiple of these correlations. All these correlations are significant with this p less than 0.05, so it's actually only significant correlations, right? And for example, here you can see the whole block of negative of exercise measurements, frequent exercise measurements, is negatively correlated to BMI trend. It means if you do whatever exercise, most likely your weight will decrease for those who was doing. Few of them are not, but most of the sensor data, sequential sensor data representation will just do some exercise.
Is it correlated with the weight or with the fluctuation of weight?
Fluctuation, BMI trend.
Okay.
Yeah, so, yeah, of course, yeah. So I actually should name it as a weight increase. Then it will be much simpler. I call BMI trend, it is confusion, yeah. And we have other interesting things like some interesting image concepts related to BMI trend and these kind of things which is related to places where a person goes. For example, you can see that home, store, furniture, as well as ice cream shop, as well as spa, positively correlated to increase of weight. So if you go spas and home stuff, ice cream shop, then most likely it will be a reason. And this additionally shows that it makes sense to do this kind of research, and it makes sense to build the models that integrate this kind of multi-source data, combine it together, learn from them jointly, and perform very nice results. This is, so far I see the first time I was doing that, combining all this and looking for this correlations. And it's a few chapters in my paper related to this, so you can just go back and read. It's called Treat Can Be Fit, the genetic paper. And this is cross-source correlations. Probably I wouldn't stop here to say that. Just basically to show that features themselves also significantly intercorrelated. Here all circles are those who significantly is the negative or positively correlated. So all of them are intercorrelated. That helps us to testify, to explain why we build this kind of models. So from these two talks, I hope we learned that multi-source data is essential for so many applications in computer science, for sure, and social science applications as well. We learn how to represent the data, we learn several applications, we learn that it's related to our physical cells, we learn how to measure the distance between different social networks in terms of clustering. And you see some nice plots that could be further research, it could be one research project for you in this summer school, which is again very doable. If somebody can explain it, I would be so happy to know everything. We can work on it further. In fact, I work with my social scientists deeper on this kind of data sets, trying to explain this kind of relations. This is all works, more or less mentioned in this tutorial. You can ask me about any of these works and talk further. And there are several data sets. Yuri, can you help me? Would be somebody explaining the next part of the data set?
Yes, correct to me.
Yes, I told the problems. I hope you will come back in.
Okay. Okay, so I will talk about mine.
You have half an hour to explain your data sets in detail.
Also, I shouldn't be so fast.
First of all, we have a coffee break now.
Maybe
Yes.
we have my explanation, so I think in the lecture when Sergey comes, he can explain his.
No, I think the better is to make a coffee break now because I think everybody would like to have a little break, and then in the beginning of
guys, who was for coffee break? This takes 5 minutes.